Okay, this is problem 1. And in this problem, we've got an electron in an infinite one-dimensional well. Initially, it has length L, and we're told that the ground state energy is given by E1. And we know that for infinite potential wells, the energy levels are given by h squared over 8mL squared n squared. So for the ground state energy, we've got n equals 1. So this is equal to h squared over 8mL squared. So the length of the well is then changed, so L goes to L dash, and it gets a new ground state energy, E1 dash, with the new length, h squared over 8mL dash squared. And we're told in the question that E1 dash is equal to 0.500 E1, which is probably easier to deal with a fraction, so we'll put this as a half E1. And what we're asked to find is, well, what's L dash on L equal to? We want to relate the new length to the old length. So what we can do is substitute these two expressions here into this equation here. So we've got h squared over 8mL dash squared is equal to 1/2 times E1, which is h squared over 8mL squared. So here the h squareds are common, the 8m's are common. And what we're trying to get is L dash on L. So let's put L dash squared on L squared. And we've got a half on this side, but if we multiply both sides by 2, we'll get rid of that half. Okay, so 2 is equal to L dash squared on L squared. So L dash on L is equal to the square root of 2, which is equal to 1.41. And there's no units because it's just a ratio of 2 lengths. Problem 2. So in this problem, we once again have an infinite potential well, and we're asked to find the ground state energy of an electron and a proton. So we're going to need to use our equation that the energy is given by h squared over 8mL squared times n squared, and the ground state occurs when n is equal to 1. Okay, and we're told in this case that the well is 200 picometers wide. So L is equal to 200 picometers, which is equal to 200 times 10 to the minus 12 meters. Okay, so for an electron, we've got E1 is equal to h squared, which is 6.626 times 10 to the minus 34 squared, over 8 times m. Now for an electron, this is the mass of the electron. So that's 9.109 times 10 to the minus 31 kilograms times L squared, which is 200 times 10 to the minus 12 squared. Solving this on the calculator, we get 1.51 times 10 to the minus 18 joules. Now, more common units to use for these types of energies, just because it's better unit for things of this size, is electron volts. So if we want to get this to electron volts, we divide by the charge in an electron, 1.602 times 10 to the minus 19. And when we do that, we get 9.40 electron volts. Okay, part B then asks us to calculate this for a proton. So proton's the same apart from the mass. The mass of a proton is heavier. So we've got E1 is equal to 6.626 times 10 to the minus 34 squared, and then we divide by 8. We've got the mass of a proton here, 1.673 times 10 to the minus 27 times 200 times 10 to the minus 12 squared. And solving this, we get 8.20 times 10 to the minus 22 joules. And then if we want to put it into electron volts, we just divide by 1.602 times 10 to the minus 19, and we get 5.12 times 10 to the minus 3 electron volts. Okay, so this is problem 3. So in this problem, we've got an electron trapped in a one-dimensional infinite potential well with a length of 250 picometers, and we're asked how much energy it needs to absorb to jump from the ground state, so from the state with n equals 1 up to the state with n equals 4. And we know that the energy of the states in an infinite potential well is given by h squared over 8ml squared times n squared. So the energy it needs to absorb is given by the energy of the excited state, the third excited state, minus the energy of the ground state. And so this will be equal to h squared over 8ml squared, and here n is 4, so that's times 4 squared, minus h squared over 8ml squared times the ground state, which is 1 squared. So this will be h squared over 8ml squared times, this is a common factor, so I've taken it out the front as a common factor, and then we've got 4 squared, which is 16, and 1, so minus 1. So this is equal to 15h squared over 8ml squared, and now we can just substitute in. So we've got 15 times 6.626 times 10 to the minus 34 squared over 8. Now it's an electron, so the mass of an electron is 9.109 times 10 to the minus 31 times L squared, and L is 250 picometers. So it's 250 times 10 to the minus 12 squared. Solving this on the calculator, we get 1.45 times 10 to the minus 17 joules. And so this is equal, well, that's the answer. But if we want to put it into electron volts, which is a more common unit for things of this size, we divide by 1.602 times 10 to the minus 19 and end up with 90.3 electron volts. This is problem 4. So in this one, a particle's confined to a box. So the particle's between minus L on 2 and L on 2, and it can't be outside that. So in order to do that, we're going to have an infinite potential. So outside the box, we'll have a potential, an infinite potential, and inside the box, 0 potential. So what would the potential look like in this case? This is what the potential would look like. Now in part B, it says what's the wave function going to be at the following locations. Okay, because it is definitely inside the box, it has to have 0 wave function at minus L on 2 and at L on 2, and also outside the box. So all of these are 0. It's 0 when it's less than L on 2, it's 0 when it's greater than L on 2, it's 0 at exactly minus L on 2, and it's 0 at exactly L on 2. So all 0. And then we're asked for what's the value of minus L on 2 of psi of x squared dx. Now this is the probability that the particle is inside the box. We know the particle is in the box, so that tells us that the probability of this happening is 1. So the value for this is 1. Okay, so this is problem 5. So in this problem, we've got an electron which is initially trapped in an infinite potential well. So it will have some ground state, E1, with some wave function, which looks something like this. And then we're asked if the potential of these walls is now decreased. So now rather than being at an infinite energy, the potential's at some energy U, which is less than infinity. And we're asked how does the wave function of the ground state change? Okay, so when the potential decreases, it's possible to have some of the wave function outside the well here. So it dies off very quickly, exponentially, but the wave function will look something like that. So because it's going outside the well a little bit, the wavelength of our wave function is going to increase, so our energy is going to decrease. So the energy of the ground state will decrease. Things with a longer wavelength, like red light, has lower energy than blue light, which has a shorter wavelength. So the energy of the ground state will decrease, the wave function penetrates the walls of the well. Now, for the higher energy states, it depends how much higher. If the energy of the levels is less than U, then we'll end up with slightly lower energies than with the infinite well, but essentially the same. But once again, they will penetrate the walls, but they'll quickly decay once they get there. So if En is less than U, the energies are a little lower than for the infinite well. The wave function extends into the well. And then if the energy of the state is greater than U, it's no longer quantized. That electron is free to escape, and it can be absolutely anywhere. So the wave function's got the same value everywhere. We don't know where it is. So if En is greater than 0, no longer quantized, the wave function is everywhere. So it's got a very low value because it's everywhere.